Okay, well, welcome everybody to this week's Philosophy of Physics seminar in week 5 of Trinity term. And today's speaker is Nick Huggett. Nick is LAS Distinguished Professor at the University of Illinois at Chicago, but perhaps more importantly, a former physics and philosophy undergraduate of Oxford. He's, of course, very well known to most people here as someone who's written extensively in philosophy of physics, lots of different topics in things connected to space-time, the early modern absolute relationist debate, quantum indistinguishability, and in the last decade or so, he's been involved in a joint project with Chris Woutrick, which has been tremendously beneficial, I think, to the field. Several early career researchers have benefited from that project, including some people in the room as visiting postdocs and PhD students. So, Nick, it's a great pleasure to have you here speaking on quantum gravity in a laboratory.
Thank you very much. Thanks, everybody. Yeah, no, it's really nice to be here. So I really appreciate that. And yeah, so looking forward to talking about this today. It's about some very new physics I want to explain to you, and then talk about some of the philosophical issues that it raises. So I should say first, as it says on the slides, that this is based on joint work with Niels Linnemann and Mike Schneider. So there's actually a long paper that we posted finally on the archive last week, and that's the link that you see there if you're interested in reading the much longer version of this. I should say this paper has been something of a negotiation. We actually have rather different sort of views on things, and so I mean, everything that's in the paper we all agree on. I think we learned a lot from each other, and I think Mike's probably there. I'm not sure if Niels could make it today. So I thank them a lot. It's been a real education, and I'm very happy with the way the paper is. But I should say the things I say today, they may or may not agree with the exact way I say them or the exact kind of emphasis. So more than the usual disclaimer that all the good stuff is to them and all the bad stuff is for me, don't necessarily, or ask them before you hoist on them the things that I'm going to, the claims that I make today. They may or may not agree. Okay, without further ado, as you can tell from the title, the topic of the paper is about attempting to perform experiments to learn something about the quantum nature of gravity, or quantum gravity more generally. So by way of introduction, I'll start with the sort of usual disclaimer that's made in such talks, and often talks about quantum gravity and philosophical company in general, is to sort of note how hard it is to test the predictions of quantum gravity. So I hereby note that, but importantly, immediately want to mention a number of very important caveats and emphasize the novel in the heading of this slide. Of course, quantum gravity is supposed to recover ordinary quantum mechanics in the appropriate limit. It's supposed to recover ordinary general relativity in the appropriate limit. So insofar as those are logical consequences and predictions in that sense, of course, there are predictions of quantum gravity that you can test. In a way, that's a theme that's been recently, I think, in sort of very nice work, taken up and extended by David Wallace. That's the W21. Oh, by the way, for people in the room, there's a link for the slides if you want to have the whole slides. All the citations are on a page at the end. For people who are on Zoom, I put the slides in the link in the chat, so you can use that to follow along or skip ahead if I go too slowly, or however you like. So whether it's hard to test quantum gravity, one way of putting David's point is it depends exactly what you mean by quantum gravity. he talks about low energy quantum gravity, quantum gravity as an effective field theory, and sort of talks about quantum gravity within the effective field theory program. And then there are even more tests of quantum gravity in that sense, in the sense of verified predictions. We use, as he says quite correctly, the mean field semi-classical sector of quantum gravity all the time, and that definitely takes us beyond quantum mechanics on its own or general relativity on its own. So that's tested. Pushing a little bit further, and I'll come back to semi-classical gravity, that'll be part of the talk today. Actually, more than semi-classical gravity, where we take a mean field and so treat the gravitational field ultimately as a classical system. In a small part of the paper, but I think an important part to look at if you're thinking about these things, he does discuss the inflaton field account of structure that's observed in the cosmic microwave background. And as he says there, so I don't fully understand the physics here, but I think he's quite correct in what I've looked at, that actually it's not enough to just have classical space-time in that explanation. One explicitly takes space-time to be in a quantum superposition. So in a sense, if you buy the inflaton account of this structure that's observed in the CMB, then that already is an observation of the quantum nature of space-time that's quite strongly related to the kind of experiment I'm going to talk about today. So yes, maybe that's already part of it. What I want to address today then is an experiment that is proposed and argued to observe, let's say for now, the characteristically quantum nature of gravity, to actually see if we can probe the quantum character of gravity. So in a way that we don't in the mean field approach. Okay, so you might start, people have thought for a while, often people go back to Feynman in the quite many decades ago, thinking about this kind of question, how one might do this. Of course, the first thing that might come to mind is, can you perform some sort of gravitational version of the photoelectric effect? Okay, when you're in high school and you first come across quantum mechanics, that's what is pointed out for electromagnetism as showing its quantum nature. But it's quite clear that that's not a feasible, really ever going to be a feasible experiment for gravity. I did this little calculation. You think about hydrogen, you think about the gap between the N1 and N2 electron bands. It's 10 electron volts for the electrical potential energy, but the gravitational potential energy is 10 to the minus 38 electron volts. So vast orders of magnitude different. You're not going to sort of produce detectable gravitons from these transitions. Okay, that's not going to work. Something that seems more promising would be to take a material superposition system in a quantum superposition, let it interact with the gravitational field, effectively become entangled with gravitons, and then see the decoherence that causes for the material system. I don't have the numbers for you, but still a very, very sort of delicate and hard experiment to undertake. So the kind of experiment people have been talking about for about the last 5 years now, and has caused quite a lot of excitement in both theoretical and experimental communities that are interested in this sort of thing. And that's what I'm going to talk about today, is in the study of gravitational Schrodinger cats, or grav cats for short. Not a terribly pretty expression, but it's a convenient one, as you'll see. So I'm going to, of course, talk about these in more detail and exactly what this experiment looks like. But what you're supposed to imagine is a system that's small enough that can be put into a quantum superposition and kept there. It doesn't interact with its environment too rapidly to decohere quickly, too quickly to perform the experiment. But it still has to be big enough, heavy enough that it's actually experimentally possible to detect its gravitational effects. And of course, there have to be no other kind of van der Waals charges or any van der Waals forces that are greater than the gravitational effect. So remarkably, and that's what's sort of motivating things, interest in this, experimental physics has got better and better at putting larger and larger objects into superposition. So on that side, we actually can put into, I can't, but experimentalists can put into superposition larger and larger things, so that we're coming up that way. Similarly, there are lots of experiments that work on very small gravitational fields and measure the effects of very small gravitational fields. And so the gravitational fields of lighter and lighter things are now detectable. And it's hard for me to assess how optimistic or otherwise this is, but talking about maybe in the scale of sort of 10 years, these may actually meet and it'll be feasible to perform an experiment where they both meet. And if you want just a little motivation for why that actually seems kind of possible, the kind of regime in which they would be undertaken is at the regime of the Planck mass, which unlike all the other Planck quantities is of course actually kind of human scale. It's about the mass of a flea egg. 20 micrograms. So that's a very kind of human scale. That's the kind of scale at which these experiments would have to be performed. Okay, so that's the general introduction and where we're going. So 2 halves to the talk. One, I'm going to talk about the physics involved. So I'll give you a picture of how this is supposed to work. I will talk about the implications for these experiments if carried out successfully with the result expected for semi-classical gravity. Then I will look at the 2 ways people have of interpreting these experiments, the Newtonian and tripartite models, and we'll see that which way you choose to model the experiment makes a difference to how you understand its consequences, its significance. And so part 2, I will turn to interpretation, actually address the question of the title, and looking at the clock, I suspect I may not quite get onto slides part 6, but we'll see. Talk about why to perform the experiment. Okay, but I will get straight on to the physics. So let me just sort of run through very naively so you can see basically what's going to happen in such an experiment, what it looks like, and then we can unpack what's going on in 2 different ways after that. So I'll start with what I'll call the naive model of the gravcats. So the kind of the suggestion that's made in one of the papers is you suppose you have 2 100th of a microgram pieces of diamond. Maybe that's what one could carry out the experiment using, and suppose they're in a quantum state that is separable, but they're each in superposition. So the picture I have is we have 2 gravcats. There's one on the left at position -d, let's say, one on the right, position D, and each one is in a superposition of left and right parts, sort of symmetrically about D. Okay, so gravcat 1 has 1 packet at -d minus delta, and a second packet at -d plus delta, and similarly on the right-hand side. So their state is, of course, I'll write their state this way. I have left plus right for gravcat 1. I've sort of avoided putting lots of labels here. These systems will always have we'll have 3 subsystem equations in a moment, but right now there's only 2 subsystems, the 2 gravcats. Whatever you see on the left of the tensor product sign, that's gravcat 1 state. Whatever on the right, that's gravcat 2 state. And so they're each in a left-right superposition, which of course you can factor out, and then we get 4 terms, which of course individually one thinks of. The first term corresponds to 2 gravcats in the 2 left positions, so -d minus delta and d minus delta, so 2d apart. One with gravcat 1, the next term with gravcat 1 on the left and gravcat 2 on the right. So they are 2d plus 2 delta apart. And so you see these different packets end up in the different terms, end up different distances apart. They're going to be feeling different gravitational fields. Okay, so if you look at each of those terms then in the sum, they correspond to packets, gravcats at different distances. They'll feel different potentials. We'll assume nothing else is going on in this system. They're at rest. There's no other interactions. They're just feeling one another's gravitational potentials. The experiment is so quick that they don't start moving or accelerating in any appreciable way. So all we're going to be interested in is the potential, and so the phases that develop in each term. Okay, so the phase is just going to be given by the potential. So if you break it out, because the two left-hand ones would be, that corresponds to a state where they're 2D apart. As time goes on, they're going to develop a phase with h bar equal to 1, of course, of gm squared t over 2D. They're sort of 2D apart, and the left-right ones, as I said, since they're 2D plus 2 delta apart, they develop a different phase. This is the rational phase, right? Very trivial way in ordinary quantum mechanics for the state as time develops. Because the key thing is these different terms develop different phases, and that, of course, breaks the separability of the state, and it is now observably entangled. So a little more concretely, you might imagine that these little bits of these tiny diamonds have spin. You pass each one through a Stern-Gerlach apparatus up, and you let them sit like this for a bit, pass them back through the Stern-Gerlach apparatus, and now back, recombine them. Now they're no longer in a spatial superposition each, they're back in unique positions. But the result of this is going to be that their spins are now entangled, and that's the measurement you do. You would measure, you'd have you would have an ensemble of these systems. You'd measure the spin correlations between them, and exactly what you'd be looking for is violations of Bell inequalities, so that you could tell these systems had become entangled. But I remind you at the beginning, they were not entangled. So it's the entanglement that's really key here, and it's this gravitational effect that's producing the entanglement, inducing the entanglement. Okay, so the claim we're going to investigate is that I think most of the people, almost everybody who's involved in this agrees that this entanglement is what you would observe in this experiment. I won't talk about Penrose and Diosi. There are some people who probably, I think are probably committed to not seeing that, but what's generally agreed is we will see this entanglement. The question is, well, what will we infer when we see that entanglement? Okay, so one line of thought by the people who proposed this is that seeing that entanglement would then be a witness or a kind of indirect observation. Witness is the language people used here, of the quantum nature of gravity. And I've cited 3 kind of important papers here from 17, paper by Berzer and a number of other people. Second one from Oxford, from Marletto and Vedral, simultaneously proposing a very similar idea. And then the CNR that's Christodoulou and Ravelli, who we will come later to exactly how they modeled things, how their take on what's going here. Okay, so those papers claim we will do this experiment and this will witness the quantum nature of gravity. But I want to unpack what that means. So quite likely you're if you follow what I'm saying here, thinking from the way I've described things now, that's a pretty strange kind of claim, because there wasn't anything in the analysis that I gave you that seems particularly quantum about gravity. We just had a superposition of gravcat terms and put in what seemed like a classical potential. There's a hat on the potential, right? I mean, it's got to be a quantum operator, but I think a reaction from the way I would have presented it so far is this doesn't show anything tremendously quantum about gravity. So we need to unpack why this claim is made and some evaluation of, you'll see where I go with that, what we should say about this case. Okay, Good. So first of all, here is some nice way in which you might say this is quantum. You might ask, well, what if we tried to model the situation, GravCats, using semi-classical gravity? So thinking in terms of the Einstein-Müller-Rosenfeld equation, where we take Einstein's equation and replace, we now have quantum matter. What are we going to do? Well, we would just replace the stress energy tensor on the right-hand side with the expectation value of the quantum, of the stress energy operator for the particular state of matter, and see where we go with that. And the key thing is, if that's what you think of by gravity being classical, then this won't work. If you see the entanglement, then this process won't produce it for you. So at very least, you're ruling out semi-classical gravity. Okay. I mean, that's partly interesting. Well, it's interesting to me because 20 years ago, I wrote a paper with Craig Callender where we said, no one's disproved semi-classical gravity. So that's one of the reasons I got interested in this, because this really would. So again, do a Newtonian analysis, so ignore self-gravity. And now what we have to do is take the expectation value of the stress energy, which amounts in this case to just taking the expected position of taking the expected position of each particle and then considering the gravitational field due to that position. We're working in a Newtonian way. So the expected position of the GravCat on the left is at minus d, and that on the right is at plus d. So no, it's a little faint, but now you can see what potentials each of the terms is going to experience. So a GravCat in the left position for GravCat1 is of course 2d plus delta away from the expected position of GravCat2, whereas a GravCat in the right position of GravCat1 is rather closer. So it's going to have a potential corresponding to a GravCat sitting 2d minus delta away. It actually does, if you think about it quickly, it doesn't actually matter exactly how you decide to take the expectation value here. Once you've taken the expectation value, the point actually is going to be that the left packet of GravCat1, say, is going to see the same potential in every one of those terms that it appears. Same for the right packet. But you can see it in this case. I've kind of colored coded things so you can see how it goes. Okay, if you now write in these potentials, this is always going to go with the left. The left part of GravCat1, VL2 is always going to go with the left part of GravCat2. But because these potentials now just track each of the left-right components, and since the thing was separable to start with, it's still going to be separable afterwards. We're just going to pick up factors, new factors, and you can check. Again, if this is too quick, slides are here, you can look at it, you can download the paper. It's very easy to see that this is just going to factorize in the most obvious kind of way. And so this is not an entangled state. When you do the experiment that I described, and you won't find violations of Bell because it's not entangled, it's a separable state. Okay, so that's the bottom line. Semi-classical gravity won't give you the predicted entanglement, and so people expect this is the experiment that will rule out semi-classical gravity. I will pass over the Page and Gailker experiment. There's more controversy about whether that actually does the job, if you know about that. Again, Wallace argues quite strongly that it does, but it hasn't had the impact of this experiment. Okay, so that's sort of a sense in which we've now seen that gravity is quantum, perhaps. But it's just in terms of ruling out semi-classical gravity, this particular option. So I think there's a lot more still to unpack about whether this really amounts to seeing gravity behaving in a quantum way rather than not in a semi-classical way. Moreover, although papers often sort of start by saying, yeah, people have the idea that something like semi-classical gravity is a live option, or again, Penrose DOC, something like that, where another way of keeping gravity classical. I think that sort of similar considerations will be a problem for that theory as well. Seems my anecdotal sociology tells me that very few people in the theoretical quantum gravity community really think that those are serious options in the first place. So there is a bit of a question here about why does it matter to rule out semi-classical gravity so much? That may not be enough of an argument to motivation for actually carrying out these experiments. So that's a question made to return to at the end, and certainly talk about when we talk about it in the paper. Okay. So let's think. So that's the one definite thing, I think, pretty uncontroversial thing we can say so far about what this would show about semi-classical gravity. But I want to explain now the debate about, or the different feelings people have about whether we would really have seen the quantum nature of gravity. So I'll start with the side that is skeptical of that claim and talk about how to understand what description that side of the argument thinks you should give to gravcats. So natural thing to do is, okay, let's start with the sort of more fundamental physics, unpack things from there. I've written down a very simple non-relativistic model, but it seems to understand what's going on, we want to sort of start from a more fundamental starting point. And well, there's sort of no more fundamental starting point that we have at the moment than starting with basic, standard ideas of quantum field theory and general relativity. So here's a derivation. This comes from a paper by Anastopoulos and Hu. You can see it's from 2014, so it wasn't responding directly to what I've been talking about, but to other sorts of ideas about how we might come up with a classical-ish kind of gravity. And anyway, yeah, in fact, that if you've followed this at all, that it's a paper critical of the Newton-Schrodinger equation and why it's misguided. If you don't know what that is, that's fine. Okay, so write down, the idea would be to write down a gravitational action. So the sort of simplest thing that you could use to model this would be to have scalar matter, linearize in Minkowski spacetime, gauge fix as necessary, and the sort of standard prescription would lead you to a Hamiltonian like this, where we have a Hamiltonian for the scalar field. We have a so epsilon is the matter density. So this is the Gauss constraint that arises from the gauge fixing. And then what you have after that are additional perturbations around that solution, especially this first term. The gammas then are perturbations in the metric and include the transverse traceless parts of the metric. So gravitational waves, the things that are going to be gravitons when you quantize, they appear in these terms here. And then there's self-interaction between the gravitons as well. But Tij is the stress energy. So this term here in this integral represents the interaction of the gravitons with matter. Good. But we're working in the static Newtonian regime. And so we don't care about the interactions. So we throw away the Klein-Gordon, the Hamiltonian for the matter field. And the graviton terms, the graviton corrections don't matter for this calculation. So one throws all of this away. Oh, I didn't mention the ellipses, that's higher order corrections, of course. The only thing that actually matters in the derivation because remember, ultimately, all we want is that Newtonian potential is this Gauss constraint. This is the only term that actually appears. So there must have been a slide earlier where I defined GIE. I'm sorry if it wasn't, but it's gravitationally induced entanglement. So that's the name given. People are sort of closing in on as the name for this kind of experiment. Okay, so once you've done that, you perform quantization, and of course, basically what you get is the Hamiltonian being, you know, GM squared over the position, the difference in the position, the separation, which is just giving us back the Newtonian potential that we just naively appealed to in the naive model. So if you go the standard route of gauge fixing, quantizing, and Anastopoulos and Hu say if you go the other way, quantize, then gauge fix, you get to the same position as well. You get back basically to the Newtonian model. A little more carefully, because I do want to distinguish the naive model from the Newtonian model. The equations, you know, the bottom line equations and picture are the same, right? The difference is the naive model, well, we just did the naive thing, we just plucked it out of the air. The Newtonian model you want to think of as, you know, the same basic equation, but actually with this in the background, it's coming from applying quantum field theory techniques to general relativity, you know, in the static Newtonian limit. Okay, so of course, the Newtonian term that's left over, here it's arising, you know, for emphasis from the gauge constraint. And of course, it's fully determined by the instantaneous matter distribution. So if you're thinking about this in gauge field theoretic terms, and say the way one would talk about it in a textbook on gauge field theories, the true degrees of freedom, the things that are called the true degrees of freedom, the perturbations, they're all gone. The gravitons are gone. And so this is one of the motivations, right, people then have for saying we're not seeing the quantum nature of gravity at all. So it's more than just saying, well, look, you've just written a V with a hat. It's really based on an idea that there are, you know, the true degrees of freedom, and they're just not playing any kind of role here. So, you know, it's the gravitons. We'd have to actually see gravitons doing something in order to actually see the quantum nature of gravity. Okay, we'll unpack the argument a little bit more and maybe talk about it. Maybe I'll just flag work is being done by that word true. One could take it strongly as all the physics is there. Maybe that's too strong. Certainly the case that it's not, you know, the gravitons are not playing an immediate role here. Okay, that 21, that's another paper by Anastopoulos, where this is sort of argued is in a paper by Anastopoulos and a couple of other collaborators. Okay, so I've given this paper a few times, and sort of different audiences seem to go different ways on this question. So I'm always kind of interested to see how people feel, because people feel pretty strongly one way or the other. And you may be feeling, yeah, that's exactly right. Okay, well, what's the fuss? There may be other people here, and there certainly are other people in other audiences that think, no, that's completely the wrong way to think about things. I don't know. I never got around to doing this. Mike and Niels always wanted me, when I was on Zoom, to actually run a Zoom poll so I could see how people were sort of falling on this question. Yeah, it's interesting. Okay, so, but the thing you might be thinking is, but look, you know, we've been learning for the last 200 years, we've been learning the real importance of the idea of a field. And, you know, 100 years ago, we learned that this was the idea for gravity. It's really a dynamical system. That's got to be taken into account. That's sort of the central thing that you need to think about when you're thinking about gravity. That's the lesson of general relativity. And you may be able to sort of think about concrete people who would be saying that at this point. gravity is dynamical and causal. That's all gone out of the window here in this description. If you actually really want to model the situation properly and think about what this is showing, you've got to put that into the picture. And we can do that in a pretty simple-minded way. And that would be, look, gravity is not just a kind of, fixed rod like this potential that's pushing between things. It is a dynamical system on the same footing as the gravcats. And we need to represent that. And so we kind of made a mistake right at the beginning by writing our states down as bipartite states rather than tripartite states. There really are three subsystems here. There's the two gravcats and there's the gravitational field. So I'll change my notation now in sort of in the obvious way. On the left, we have gravcat 1. On the right, we have gravcat 2. And then in the middle, there's a state representing the appropriate gravitational field. And you'll see the gravitational fields, are different. When I have both, if I had two gravcats on the left, I would have this gamma LL field and so on. Okay. So concretely, what could these gammas be? Well, you might want to think in a geometric way. These could represent classical states of the gravitational field, or be labeled by classical states of the gravitational field. Well, if you're working in GR, say, and there are other options I'll mention in a minute, well, the metric you'd write down is the appropriate one for the static Newtonian limit, which is the one that I've written down here. Inside and out, you're imagining the gravcats having finite radius, and inside and outside refers to whether you're inside or outside of the gravcat. That's the metric that one would write down. Let me just, before I read this point, let me note that, again, one is basically making the same move as one did thinking about the Newtonian model. Go back to to more fundamental physics. Again, start with general relativity. That's what we're doing here, and thinking about it from a more fundamental point of view, what's going on in this experiment. Okay, this is the route that Christodoulou and Ravelli, that in the paper I mentioned before, take in their analysis of the situation. Because now you see each one of these terms corresponds to a different gravitational field, and now you can calculate the proper time along each trajectory, each gravcat pair takes through its geometry. But they're different geometries. There's going to be time dilation effects, and it's not hard to calculate it. They do in their paper that, you imagine each one of the gravcats because of its rest mass, has a little clock. That's where the phase is coming from. So all that matters is the different proper times. And the differences in the proper times turn out to be exactly the phase differences that we calculated before again. Okay. So we're going to get relative phases developing in just the same way. They're going to be exactly equal to those of the Newtonian model, so of the naive model that we looked at before. Great, so that's the prediction, it works out. But now I can look at my equation here, and clearly this is not separable in the gravitational field. This is, this is a, sorry, I don't mean separable. This is a superposition of different states of the gravitational field. There you go. My tripartite state looks like this. I've got different gravitational fields. Gravity's in a superposition here. You can see it from the equation. Okay. Not just gravity, but before certainly matter was in superposition, but now we have gravity in superposition from this point of view. And again, that kind of comes again from thinking gravity has to be represented as a dynamical state. And that is motivated by, of course, space-time causality, and the geometry, changes in geometry have to propagate causally. And so it has to be dynamical. And so we're led to this tripartite picture, which gives us the quantum superposition. Okay, well, a few things that need to be sort of added to that. Can actually tighten. There's a way in which the way I've put it so far is loose and needs to be sort of tightened up. So, first of all, as I said, I motivated this approach with appeals to space-time causality, so that the gravity had to be a dynamic system itself. That's not actually logically necessary. Mike really took the lead on this. You can do the same analysis in Newton-Cartan gravity, which is really not dynamical, and you get the same predictions out as well. But the same picture, you have a superposition of different states of the Newton-Cartan gravity. So in some sense, what's motivating this, one way to motivate it is through space-time causality. A little more carefully, what's needed to motivate it is that the idea is that there's no direct interaction between the two gravcats, but gravity mediates the interaction between them. And that has a technical meaning. Write down the Hamiltonian, there's no direct interaction term between the gravcats, only between gravcats and gravity. Okay, so that's really what's going on here. Yeah.
In this last comment that the Newton-Cartan gravity, although there won't be a time dilation as a way of recovering the original naive relative,
There's going to be a difference in the
yeah. It's going to be some other thing which will give the very same relative phases.
You pick it up right. Look at the papers. There's a difference in the energy energy of the particles.
But the experimental statistics expected in your lovely Stern-Gerlach way of probing the relative phase differences, those predicted statistics would be the same for the Newton-Cartan as for this.
You would get exactly the same phases as before. I mean, that's not hugely surprising again, because there aren't a whole lot of things with the right dimensions that you could even write down. So, but yeah. So it's not a relativistic effect, I would say. Yeah. The Burza paper, they didn't think of it in either of those two ways. They were actually envisioned there being they were thinking in a quantum field theoretic way about there being a coherent state of graviton's field that was mediating this interaction. But as I say, all of these pictures just have in common that you have to think that there's no direct interaction between the gravcats. It's always, they only interact with the gravitational field. Now, I gave an intuitive argument for, look, it's point at the equation and say, look, they're in superposition, you can see it. That's maybe a bit too quick, because you might think, yeah, but there are ways of writing classical states down in quantum theory. I can still have states. Usually the way people would think about it is that gamma might be classical if it doesn't have any non-commuting variables. So essentially only has one operator, only one operator or something like that. But you can actually tighten things up. I mean, this line of thought takes you into quantum information theory, generalizations of that. So theorems proved in constructor theory, the local approach to generalizations of quantum information theory. People have proved results, similar results, or related results in generalized probabilistic theories. So it's quite easy to do. So in the paper we give, we sketch a proof in if you assume quantum mechanics. But basically, if you have two quantum systems that can only interact, they can't interact with each other, but they can only interact with a third classical system. So two qubits and a bit, where a bit, as I say, only basically has one observable up to a scale. Okay, there's no way that the two qubits can become entangled with each other if they weren't originally. It's pretty sort of fairly easy to see that. In quantum mechanics, it's sort of trivial because in a sense, they can't even see each other at all. That's why the generalizations are nice. But the generalizations aren't quantum mechanics. So strictly speaking, what you show is not that gravity has to be quantum to produce the entanglement, but that it can't be classical. These other theories, their whole point is to kind of generalize quantum mechanics and have other alternatives between the quantum and the classical. And that's really the content of the theorems. Right. So that's, again, Marletto and Vedral in a couple of papers. And then Giacomini and a couple of her collaborators, Selby, and I'm sorry, I'm forgetting the other G, proving these results. So they have the idea that we're witnessing the quantum nature of gravity, or rather the non-classical nature of gravity, in the sense that we just couldn't obtain and couldn't observe this entanglement if gravity was classical. Okay, so, you know, there's theorems, there's derivations. In this way, gravity simply can't be classical if it's doing all the mediating. But I can do it just with the potential and the hat as well, right? So, okay. So what's the right way to sort of think about this? Two different models with rather leading to very different interpretations of the GravCat experiment, and especially on the question of whether anticipated GravCat entanglement would be a witness for the quantum nature of space-time. Sorry, I will review and then I will sort of say what we think about this. So in the Newtonian model, of course, GravCats don't witness quantum gravity, since only the gauged fixed term plays a role. So, you know, that's the equation you want to have in mind, sort of picturing what's going on in this case. But on the tripartite model, you know, if gravity is the intermediary that's mediating the interaction between these two, the two GravCats, then it has to be quantum. And, you know, there's more to it, but naively, yeah, you can see that's the state you get, and clearly gravity is in a superposition. So of course, when we get the entanglement, gravity must have been in a superposition. Okay. So what's the right way to think about these things? So, right. There's really, so this is sort of the philosophical payoff of what we're talking about here, starting here. So really it's a comment on what I've italicized here, the word correct. In a sense, what I'm going to argue is you can't answer that question. This is the wrong way to sort of think about it. And there's first step to unpacking it is that there's really two parts to it. You know, one is, you know, what's the fund? You know, people might, there might be, if you have two models of some experiment, two ways you might disagree. You might just disagree about what the fundamental physics underlying it is. Okay, so you might just, you know, so then you would come up with different stories about what was going on in the particular case. What I'm most interested in, and that's, so in the paper, you know, that kind of thought is definitely, we trace out. There's another kind of disagreement, which is, even if I agree on the fundamental physics, how I go about, you know, taking approximations, making idealizations to derive a model for this simplified system, the Newtonian static limit in particular here, right? There are different ways to do that, and I can end up in different places with different ideas about how to model it. So in some sense, it's going to be unpacking the different sort of commitments that lead to those different places. So I would say I've tried to trace out, you know, what the theoretical, you know, starting points of these two models is. And they both seem perfectly reasonable, right? The way we started in those both seem like really important and good ideas about how you should start doing it. So it seems that the situation is going to be theory laden. So what I'm going to do is try to clarify the competing theoretical perspectives. Okay, so we can sort of think this through a bit more and see where it takes us. And in particular, kind of give you some arguments for my position, our position, that there's really, it's not something that can be kind of resolved in a way that would really produce an answer to the question of which, an unequivocal answer to the question of which is the correct way to go about this. So let's reconstruct the competing assumptions. Of course, that's a large part of what I've been doing already, and then ask whether they settle the debate. And well, there's no point giving you a spoiler alert because I've already spoiled it. So no, So back to the Newtonian model, and again, thinking about the sorts of assumptions that go into this. So basically, its assumptions, as we've seen, are standard methods of gauge quantization, both formal, but also, depending on how you want to push the argument, aspects of the law about what the formalism means to general relativity. The observation is that the true degrees of freedom do not play a role, and the whole effect then is due to a Newtonian potential. But here's where we need to be careful. As a mathematical statement, these things are completely true. But there's an interpretational step, and I'm not telling you anything sort of that I haven't said before. This is the crossing out, the red crossing out in the equation in the Hamiltonian that I wrote up. Okay, that's all that's going on here. That's quite correct. There have been arguments that have pushed that further and read something very strong into the idea of a true, what a true degree of freedom is. One should not think that the true degrees of freedom are where all the physics is. That's a further assumption from the mathematics. All right, so one could try to run this argument by thinking, look, as I said, that the gauge part, that's all just sort of conventional fluff. All the real physics action is in the true degrees of freedom. But that's not really the right way to think about things. That's to read too much into the idea of a true degree of freedom, which is pretty obvious. First of all, how you split into gauge versus, I said free, but so dynamical is really what I mean there, is partially dependent on the choice of gauge. So what you couldn't really have physical or non-physical being gauge dependent. You're shuffling between, between gauge and non-gauge. And of course, just think about the different potentials that you can have for different matter distributions. They're different and they have different physical effects. They're clearly physically different, even though they're fixed by matter. And so, of course, they're carrying physical information, even though they're gauge terms. And of course, if you think about it, that must be the case because, up until the beginning of the 20th century, all we had was the Newtonian potential, and it would be sort of absurd to think that Newtonian gravity was unphysical. That's the only part of gravity we actually had at that time. So don't read too much into that word, true. I think I spelt it right now, Jeremy. Thank you. So I did revise some things in response to our discussions. Thank you. Okay. Good. It's an equivocation on true. It's sort of equivocating between dynamical as a sort of mathematical point about the way you formulate, the way you've gauge fixed versus, real, physical, that kind of thing. But still, I've still only got the V with the hat at the end of this. And so is that quantum? Especially it doesn't have the gravitons that we would think were definitely quantum. It's gauge, it's not dynamical. So somehow the worry, the very strong argument fails, but that concern is still there. So let's turn back to the tripartite model. And actually, just looking at the note that I made myself. I'm pretty sure no one would think that if all you could say was that we had the V hat, that was seeing that was seeing the quantum nature of gravity alone. No one's going to agree with that. I mean, it's important for the tripartite model that that's not the way you model things. No one's going to sort of think putting the hat on the V is giving you quantum, showing you something quantum about gravity. Oh. Okay, and of course, the key theoretical idea in the tripartite model is that gravity is an intermediary subsystem motivated by space-time causality, but that's not the only way to motivate it, as we discussed. So let's think about, that assumption. So you might try to resist this. You might try to be, it's where this is sort of coming from, is thinking about, for instance, applying effective field theory methods to general relativity. That would tell you that, gravity had to be a kind of quantum system that we'd be writing this way. So you might have skepticism about that. You might just be sort of neutral about that. And to back that up, although Wallace's argument is, look, there's lots of predictions, tested predictions of low energy quantum gravity of EFT GR. Quite true. But outside the semi-classical regime, maybe that one thing that I mentioned at the beginning to do with the CMB data. So we really are probing a new place, and you might, that might be the point at which you either wanted to get off the boat with low energy quantum gravity, or you at least were uncertain enough to really be committed to it at that point. Mike has sort of emphasized this kind of attitude, and I think makes a very nice point that especially if you were an experimentalist rather than a theorist, you might feel less inclined that you had to have a strong kind of commitment to some theoretical attitude here. So that might be possible. You might be more radical, and for instance, Penrose Diosi might have in mind here and say, yeah, no, it's really just wrong. When we reach this regime, no way. I have an alternative theory. In fact, I'm not just neutral. I think the EFT approach to GR breaks down here. So you could have that sort of attitude. And then you would be resisting the tripartite assumption. But as I've said, that's not, neither of those, I think, amongst theorists, and the emphasis is on theorists again, rather than experimentalists, that's, I think, is not a widely accepted sort of viewed attitude. And indeed, low energy quantum gravity is widely accepted to be valid in this regime. Okay, as I've sort of noted, before, the key thing, however, is just this idea that the gravity is the only thing mediating interactions between the gravcats, and they don't interact directly. So that's actually a weaker assumption than low energy quantum gravity, the EFT approach. And that's enough, as I've sort of indicated on one of the on the previous slides, to show that if you observe the entanglement, then gravity must have been in a quantum superposition, or at least not in a non-classical state. So one would really have to deny that in some way to resist the logically to resist the conclusion. Nevertheless, and this is the way I sort of suspect a lot of people are thinking about this. Even if you were fully signed up to EFT quantum gravity, GR, you could still be thinking, as I indicated before, that doesn't commit me to one particular model or the other here. There are other assumptions that are going to go into this. And the question is not about the fundamental physics, but the right way to model this particular situation given shared fundamental physics. Okay, and so I think it would be perfectly reasonable to say yes to EFT approach to general relativity, but think, no, but the Newtonian model, that's the right way we should be sort of modeling things here. So sort of quick arguments for that, because I know we must have started a couple of minutes late, right? So I will take those, and I think I have one short slide after this. So it'll be about an hour. Okay, but sort of some quick arguments for that position. So a kind of maxim of modeling that you might have, if I have two empirically equivalent models, well, isn't it natural on some sort of simplicity grounds to prefer the model that abstracts away, simplifies away as much of the fundamental as possible? And then arguably that takes you to the Newtonian model. And I think when I talk to people who advocate something like the Newtonian model, they will sort of say, yeah, but I don't have the gravitons. There's sort of a whole load of physics I'm leaving out here. So this is really the way we should be doing it. We shouldn't put more into the model than we need to. And then again, I do come back to the fact that gravity is sort of just a gauge constraint, not dynamical. That is a math, that's a fact about how we do this. Sure, I know from these theorems that really, if I was going to write things out in the full theory, gravity would be in quantum, but I don't have to represent it that way in this case, and it's not natural to, because it's a gauge constraint. I shouldn't think of it as a third system, subsystem in my state. And finally, and I think this also motivates people, we've already talked, I mentioned other ways that one actually could think about witnessing the quantum nature of gravity that would be more definitive. For instance, if I saw quantum matter systems decohering and they could only be interacting with gravitons, becoming entangled with gravitons, an experiment like that people have talked about and described seems like that, okay, that would be a different case. So I like that point as well. I can sort of say this doesn't witness, but I can tell you what actually would in a convincing way. Some of you may have seen or heard or read the this paper by Belenkia and Bold and various other people that's I would say sort of put into this kind of, well, they're not giving this argument, but effectively they are describing a sort of decoherence experiment of this kind. Good. So, well, I forgot to put the slow transitions in, but just to summarize then, what we're seeing here, I say, is how to model these gravitationally induced entanglement experiments. It depends clearly on decisions about how to do the modeling. And they in turn depend on sort of various theoretical and methodological commitments that you could have. And of course, the weights that one gives to them, which is more important. What's the core thing to be saving? Do we want to focus on the gauge nature of the physics? Do we want to focus on the dynamical on the dynamical nature of the physics? And so I think we're finding ourselves in a situation where reasonable physicists who might agree about a lot, and especially about fundamental physics or more fundamental physics, can't find a common basis on which to evaluate the significance. They're just going to add things up differently, and so disagree about whether this is a case of witnessing or not. So one might reasonably describe the situation then, I'm going to back up. I might reasonably describe the situation using some Kuhnian language here. This is very much the kind of situation where I'm thinking more of the Kuhn of objectivity and value judgments than structure, maybe, where people can agree about a lot, but still their decisions are complicated enough that they end up disagreeing about some important questions as well. And so in that sense, and I think in the manuscript, in the sense that there isn't some rational argument that either side can give that's just going to show the other side to be wrong, we can indeed call these paradigms. I'm going to say one more sentence maybe. Of course, now the question is back to something I raised earlier. Why should we do the experiments? They're going to be difficult and hard. If there's this sort of disagreement, well, that's on the final slide it's giving you. Even if you came down on the Newtonian side, why you should still be excited about these experiments. But that's something for another time, maybe. Thank you very much.
Thanks. So we should take just a couple of minutes break to give people a chance to catch their breath.